Long-term, heavy chronic cannabis users often present with a specific, highly documented clinical profile in modern medical literature. Psychiatrists refer to this presentation as amotivational syndrome, a condition defined by a distinct cluster of cognitive and emotional deficits. The first prominent symptom is profound affective flattening. Users experience persistent anhedonia, meaning the world loses its intrinsic emotional resonance and associative value. The second symptom is a pervasive drop in short-term memory function, specifically the brain's ability to encode immediate environmental stimuli into long-term declarative storage. For decades, the prevailing assumption in medical science has been that these cognitive deficits share a single, isolated cause. That traditional model attributes all cognitive dampening purely to pharmacology, specifically the psychoactive compound delta-9 THC, binding to receptors and disrupting the brain's endogenous cannabinoid system. However, evaluating this pathology purely through the lens of biochemistry ignores a massive variable in how the drug is actually administered. It completely bypasses the extreme thermodynamic and dense particulate realities of repeatedly inhaling combusted, completely unfiltered plant matter. A more rigorous explanation emerges in the dual mechanism model. This theory combines the top-down chemical dampening of THC with a bottom-up physical structural trauma caused by the smoke itself. Amotivational syndrome is the result of a targeted two-front assault. By physically severing sensory input and chemically blocking reward circuitry, chronic cannabis use literally starves the brain's cognitive centers. To understand the physical side, we must first look at the human olfactory system, which exists as a distinct structural anomaly compared to all our other senses. The olfactory nerve, or cranial nerve 1, is the unique cranial nerve in the human body sitting directly exposed to the external environment. This diagram shows these primary sensory neurons. Notice how the root-like nerve fibers dangle unprotected within the mucosal tissue. To carry data to the brain, these axons travel upward, passing through the porous cribriform plate to synapse with the olfactory bulb. Standard sensory inputs like vision or touch must first route through the thalamus processing gateway. Olfaction bypasses that gateway entirely. The olfactory bulb sends rapid projections straight into two deep brain structures, the hippocampus and the amygdala. The hippocampus is the primary neurological engine responsible for spatial navigation and declarative memory consolidation. The amygdala sits adjacent to it, acting as the brain's emotional processing center to assign effective valence to the stimuli we encounter. Because of this direct, unmitigated wiring, ambient odors provide a constant, subconscious stream of sensory actuation. This baseline energetic input keeps both structures stimulated and primed to process information. This unique structural layout means that the integrity of these exposed nerves is a fundamental prerequisite for the limbic system, providing the foundational energetic input required to maintain emotional resonance and memory encoding. This structural vulnerability becomes critical when we contrast the thermodynamic profile of smoking standard commercial cigarettes against traditional cannabis joints. Modern tobacco cigarettes utilize cellulose acetate filters. These act as significant physical heat sinks, absorbing a large portion of the thermal energy generated at the tip before the smoke ever enters the mouth. Marijuana is heavily consumed via unfiltered joints, blunts, or glass pipes. Without a filtration medium to dissipate that energy, the combustion enters the airway entirely unmitigated. This chart compares the thermal drop-off of those two intake methods. Unfiltered cannabis combustion can easily exceed 800 degrees Celsius during a sustained inhale, maintaining a drastically higher temperature curve. Furthermore, chronic users exhibit specific inhalation mechanics. They draw the smoke deeply into the lungs and hold it there to maximize alveolar absorption. Upon exhaling, users frequently perform a retronasal release, forcing the trapped high-heat smoke back up and out through the nasal cavity. When that thermal wave travels retronasally, it washes directly over the superior nasal conchae, flooding where those unprotected olfactory dendrites hang from the cribriform plate. The immediate biological consequence is localized thermal ablation. The recurrent application of intense heat literally burns away the superficial nerve endings. This is compounded by the heavy tar content of cannabis smoke. The sticky particulates deposit onto the mucosa, triggering severe, chronic chemical inflammation around the remaining tissue. Combining extreme thermal energy with toxic particulate load effectively destroys the terminal nerve fibers, physically severing the chemical to electrical sensory transduction pathway. This physical trauma establishes a bottom-up mechanism of sensory deprivation. Alongside the pharmacological effects, the act of smoking unfiltered cannabis physically degrades the biological wires required to transmit environmental data to the brain. While the physical burn removes the peripheral wiring below the cribriform plate, a simultaneous neurochemical assault occurs on the structures above it. Because THC is highly lipophilic, meaning it dissolves easily in fats, it readily crosses the blood-brain barrier and floods the central nervous system. Once inside, THC acts as a potent partial agonist. It rapidly overwhelms the brain's endogenous CB1 receptors, disrupting the delicate homeostatic balance normally maintained by our own natural cannabinoids. The first station impacted is the olfactory bulb. Heavy CB1 receptor expression here means exogenous THC chemically depresses and inhibits any weak sensory signals that manage to survive the thermal burn below. The second station is the hippocampus, which contains one of the highest densities of presynaptic CB1 receptors in the mammalian brain. To encode memories, the hippocampus relies on long-term potentiation, a process that strengthens synaptic connections in response to repeated stimulation. This mechanism is heavily dependent on the release of a specific excitatory neurotransmitter called glutamate. When THC binds to those presynaptic receptors, it triggers an inhibitory cascade. It actively suppresses the release of glutamate into the synapse. By starving synapses of excitatory transmitters, THC blocks the induction of long-term potentiation. The brain is chemically prohibited from encoding short-term buffers into long-term storage. The final station is the amygdala and the mesolimbic pathway, the dopamine-driven circuitry responsible for our sense of reward and emotional engagement. While acute use temporarily spikes dopamine, chronic and continuous activation of the CB1 receptors eventually forces the brain to initiate a protective downregulation of dopaminergic signaling. As baseline dopamine transmission drops, the reward circuitry is left exhausted. Behaviorally, this manifests as profound anhedonia and the flattened affect characteristic of heavy users. The nerves supplying baseline stimulation are severed from below, while THC chemically forces the hippocampus and amygdala into a depressed state from above, resulting in a total cognitive blockade. The pathology of the chronic user is driven by this synergistic feedback loop. It is a state of complete limbic starvation. At the base level, high heat combustion and dense tar cut off essential environmental data directly at the source. Simultaneously, the pharmacological action of THC locks the memory and emotional centers into a sustained state of lowered neurotransmission. Recognizing physical trauma as a primary driver of this cognitive blunting offers clear, actionable pathways for clinical diagnostics. Objective olfactory decline, clinically known as anosmia, serves as a highly accurate, measurable proxy for assessing the overall health of the limbic system. In neurodegenerative conditions like Alzheimer's and Parkinson's, this exact measurement is already utilized as an early biomarker of impending cognitive failure, often preceding measurable memory loss by years. Applying routine olfactory threshold testing to chronic cannabis users could provide objective data on the severity of their cognitive blunting. Mitigating apathy and memory loss requires looking past purely chemical receptor agonism. It demands recognizing the biomechanical reality of what happens to the brain's most vulnerable nerve when exposed to 800-degree unfiltered combustion.